I'm Jun-Ho at Siemens EDA. The work has been collaborated with ST Microelectronics. Chip package interaction (CPI) is defined as an interaction between package-induced stresses and semiconductor devices. CPI-induced stress contributes to parametric failure of circuits. Traditional finite element modeling treats a die as a homogeneous isotropic material block and cannot describe CPI stress distribution accurately. Here, we present a methodology of accurately assessing CPI stress impact on circuits performance. The tool's sign-off flow show IP placement, stress simulation, and net list back annotation with calculated stress. With this flow, a user can analyze the circuits that are placed in different stress environment inside layout. Here, coordinate-dependent anisotropic effective material properties, or EMP, is explained. In this package, we define separate blocks of C4 bump layer, dibol layer, and STI layer, and describe each material properties by employing EMP, which is based on the theory of anisotropic composite material. For each layer, entire area is divided into an equal size square bin. The layout processor calculates bin's metal volume fraction and calculates effective properties. The simulated color maps in an IP block show how EMP can make differences. In A, die BOL is represented by EMP, and in B, the entire die is represented by silicon. In 1D stress profile, large stress variation caused by local layout geometries is missing when the entire die is represented by a silicon. To avoid highly non-uniform mesh caused by multi-scale in dimension, the tool employs multi-step simulations with displacement boundary conditions on surfaces of submodeling region. These figures compare the distribution of stress component inside an IP block obtained from global scale and submodeling scale. 1D profiles of stress components show the differences on the order of tens of megapascal for the two different scale simulations. The results show that global scale modeling only can lead to inaccurate prediction of device characteristics. To analyze the CPI stress impact on the performance of the circuit simulation must be performed. This can be done by annotating hierarchic SPICE netlist with the simulated stress components of each device. We use our submodeling results that describe each stress environment and enable a user to perform accurate circuit simulation. Here is an example hierarchic netlist for ELDO circuit simulator. In the figures, tool analyzes the 4 instances of X block that are located in different layout environment. Each instance exhibits different distributions of X and Y stress components. Circuit simulations can reveal the locations where out-of-spec variations can occur. To validate the present methodology, the fan-in wafer level packaging step was simulated on a dedicated test chip. There are multiple matrices of MOS, resistor, and BJT devices across the die, And these figures show in all these devices the measured and simulated device characteristics agree well within 5%. In summary, a novel multi-scale simulation methodology for assessing performance variation of on-chip electric circuits due to CPI induced stress has been developed. Stress components simulated in device channels can be supplied to the linked SPICE simulator for performing stress-aware circuit analysis. The tool offers what-if analysis at the early floor planning step and for final design sign-off. Finally, good fit between simulated and measured stress-induced shifts were obtained. Thank you.